Okay, so like my microphone is being listened to, and it looks like my pen is working. So, I need to do something before the in there. Let's get that. Then we this add a layer so that we can keep background white. Use line anymore. Brush and black. There, where it's at. Okay. And then let's check to make sure that broadcasting go anywhere. Okay, that seems to be working. Great. And I guess we also have to send everyone in the class the link. It's not get that. Oh, oh, thank you. I'm just there. I'll get it after the live stream. Okay, so all of the tricks. Okay, so now that we've gotten that all out of the way, the first question that I got for us to do together was to draw cotangent and tangent functions. So, um, I'm going to build up to something with that, but let's start by just looking at the um, special angles for trig functions. My cursor. Okay, so our special angles for cosine and tangent, sorry, cotangent and tangent angles are 0, pi over 6, pi over 4, pi 3, pi over 2. Our special angles are going to be, for tangent, we get 0, then we get 1 over the square root of 3, get 1, we get the square root of 3, and it's undefined after that. For cotangent, we start off undefined. At pi over 6, we have a value of square root of 3. Then we have 1. Then we have 1 over the square root of 3. And then we have 0. We also know that tangent and cotangent are positive in quadrants 1 and 3, and negative in quadrants 2 and 4. So as we are rotating around As we were rotating around the circle this way, we will start off positive and go negative, then positive, and then negative again. Let's start off by graphing tangent. So, tangent starts at 0. It goes up to 1 over the square root of 3, which is less than 1. Then we get a value of 1. Here is pi over 6, pi over 4, pi over 3, and over here is pi over 2. We're undefined on that value. We have a vertical asymptote, so we're going to get a curve that looks something like that. If we continue, in the first quadrant, we get our special angle values. In the second quadrant, we're going to get the same y coordinates, but in reverse order as we shrink down from um, a y value here at 1 to a y value down here at 0. So we start off with an asymptote, but we are negative. So we will start from negative infinity. We hit square root of 3, then we hit 1, then we hit 1 over the square root of 3, and then we hit 0 over here. Okay. If we continue the curve, quadrant 3 has the same values as quadrant 1 in the same order. And for tangent, it'll be the same sign. Every trig function has the same values in quadrant 3 as quadrant 1 and in the same order, but only tangent and cotangent have them as positive values. So you get your special angles here. Then you're going to get the same special angles in reverse order in quadrant 2. Then you're going to get the same special angles in the same order as quadrant 1. But you might have to worry about sign changes because only cotangent and tangent are positive in quadrant 3. And then in quadrant 4, you're going to get the same values as on the special angle chart, but you're going to get them in the same order as quadrant 2. So for sine, our special angles go 0, 1/2, 1 over square root 2, square root 3 over 2, 1 in the first quadrant. And then in the second quadrant, they're going to hit in reverse order. In the third quadrant, they're going to hit in the same order as the first time, but they're all going to be negative. So going around the circle is going to be, for sine, 0, 1/2, 1 over square root 2, square root 3 over 2, 1, square root 3 over 2, 1 over square root 2, 1/2, 0. That gets us quadrant 1 and quadrant 2. And then as we continue around the circle, we're going to get negative 1/2. Notice it's the same value here, except negative. It'll be the same value here, 1 over square root 2, negative square root 3 over 2, negative 1, negative square root 3 over 2, negative 1/2, right, negative 1 over square root 2, negative 1/2, and then 0 again as we go around the circle for sine. Same idea for tangent and cotangent. But if you have the same order in quadrant 3 as quadrant 1 and the same sign, you're going to just repeat this same section of the graph. You're going to go up like that and have a vertical asymptote. Then in quadrant 4, as you're going around it, it's going to just be a repeat of quadrant 2. So come up from negative infinity and go up to 0. This is now two wavelengths of tangent. And it repeats the same going in the other direction. So hope that is helpful. Let's continue. So we also wanted to see cotangent, COT of x, cotangent of x. Not cosine of x with COS, but cotangent. So we remember that for cotangent, we're positive in quadrants 1 and 3. We're negative in quadrants 2 and 4. Our special angle values are going to be my back button. Go. I have my tablet set up with a different computer now, and all of my hotkeys are gone. Anyway, um, so theta, we have an angle of 0, an angle of pi over 6, angle of pi over 4, pi over 3, pi over 2. And the special angle values are going to be defined pi over square root of 3, 1, 1 over the square root of 3, 0. So when we draw our graph, start off with a vertical asymptote, then we're going to come down and eventually hit square root of 3, then 1 over the square root of 3, and then 0. After that, we have the same values as before, but in reverse order. So we're going to end with our vertical asymptote, and then we're going to come up to the square root of 3, the value 1 over square root of 3, and 0. Then the bottom half is going to be a repeat of the top. Cat is meowing for me. Hey, get food in an hour. You know that. I know. Cat is always starving. Not really. He gets the food that doctor. Anyway, so this point here is the point pi over 2 comma 0. This point here is the point pi comma, well, it's undefined, so there's no point, but it is an asymptote at x equals pi. This point is the point 3 pi over 2 comma 0, and this line here is the point x, or sorry, is a line x equals 2 pi. So these are the graphs for tangent and cotangent. I would say that the best way to practice for this, the best way to practice for graphing is going to be to go to Desmos. And I have here Desmos tab. And I would practice trying to graph our function and then going to Desmos to check it. So if we're just going to graph y equals tangent of x, this is the graph that Desmos has, and we can compare that to the graph that we came up with here. And if we look, they look the same. Mine is a little bit wider scale on the x-axis, but again, we should have an asymptote at pi over 2. If we zoom in here, we're going to see that the asymptote is between 1 and 2. It's like about 1.5, which is what we'd expect because pi is a little more than 3. So pi over 2 is a little more than 1.5. That's where our vertical asymptote should be. We have this root to the function here. And when we look at our graph, we have this root here. This should be at pi based on our unit circle. Have that hitting at the angle 180, which is pi. This is at pi 0. And we look over here, and we see, sure enough, a little more than 3. We have our root. So that looks good. Let's try looking at our cotangent graph. Vertical asymptote at 0 and at pi and at 2 pi. When we type in cotangent, sure enough, we have asymptote at 0, asymptote that's between, it's in here, about here, a little more than 3. That's at pi. We have our next root at about 5.5. That makes sense because if we take half of pi, that's about 1.5. We take pi plus half of pi, that should be about 3 plus about 1.5, which gives us about 4.5. That's right. Again, it'll be a little more because pi is a little more than 3. So we have a little more than 3 plus a little more than 1.5 equals a little more than 4.5. And then we should get another asymptote at 2 pi, which should be a little more than 6. And that's where it looks like it lands over here as well. Okay, so the next thing we have to do is learn how to transform our graphs. This should seem familiar. It's calling back some skills from our college algebra class, where we had stretches and compressions of our functions. So basically, if I have, say, well, let's start with a sine. I think that the sine just feels easier to graph. We'll learn about the stretching and compressing and shifting of sine graph, and then we'll go back and do it for cotangent and tangent. So that means that if I have like y equals 2 sine of, let's do pi over 2, start with that. Well, this is a vertical dilation. That is, it's a vertical stretch. And what that means is that we're going to take the normal sine curve. Let's do it in this color. Here's our, oh, that's maybe a little bright. Maybe we'll do it that color. So the normal sine graph, if you draw it correctly, has a vertical height of 1 off of the x-axis and a vertical depth of 1 on the axis as well. So it goes up 1 and down 1 off of the axis. This stretch here is going to, there's a way to kill auto scrolling. need to. Very annoying for it to auto scroll. Yeah, setting. Auto scroll when drawing an edge. Let's get rid of that. Should get rid of that noxious effect. Now let's see if I draw straight to the edge. No more auto scrolling. So as I was going to say, this here means that we are going to stretch vertically, doubling the height. Now the curve will go, let's go back to black. All of the places where we crossed the axis will stay the same. All of the heights that we hit will be twice as tall. And all of the depths that we reach will be twice as, oops, it's not right. Will be twice as deep. So this, because it's a number bigger than 1, is going to make the graph taller by a factor of that number. We're going to multiply the height by that. If the number were less than 1, say like if it were y equals 1/2 sine of x, what would happen is it would get half as tall. It might look like this graph, where it's half as tall, half as deep. So now this part of the graph is called the horizontal dilation or horizontal stretch. Okay. Now, we get a special formula for sine cosine, secant. There should not be any at the end. And cosecant. And we get a different special formula for tangent and cotangent. The formulas are this. The wavelength of the function is equal to 2 pi over the coefficient on the x. For tangent and cotangent, that formula is w equals pi over the cotangent on the x. So if we have sine y equals sine of 2, did I say 2 over pi? I said pi over 2. Okay. Pi over 2x. I can use this formula to figure out the wavelength. The wavelength is the distance from the top of a curve to the next top of the curve, or from the midline of the curve, skipping one to the next midline of the curve. Basically, we have to complete one full cycle going through all of the y values that the function hits until we come back to the original y value. Start it at the top, end at the top. Start in the middle. Make sure to end at the middle, but to complete an entire cycle. Can't end halfway like this. This is bad. Or we could go from the bottom to the bottom. That's also fine. But the distance from here to here on the wave is called the wavelength. It is the length of the wave. It is how far it takes to go in an entire cycle of the wave. So the wavelength for this function, we take this value and plug it in there. The wavelength equals 2 pi over 2. Dividing by a fraction is the same as multiplying by the reciprocal. So this is 2 pi times the reciprocal. 2 over pi. The pi's cancel, leaving me with 2 times 2 is 4. This is the wavelength. Or that is the distance between the trough and the trough, or the crest and the crest of this wave. So now that I know that, I can graph my function. The normal wavelength for a normal sine curve is is 2 pi. Wavelength equals 2 pi. This turns that 2 pi wavelength into 4 units. So if this is a little more than 6, now we're going to pick x equals 4 and make the wave that wide. So starting from the beginning, if I have y equals 2 sine of, let's do pi over 3x, this gives me an amplitude of 2. This value tells me how high and low my crests are, and a wavelength of 2 pi over 3, which is equal to 2 pi times 3 over pi, which is 6. And to graph this, I will now count off 1, 2, 3, 4, 5, 6. I know sine starts on the midline, so that means that after one wave, I'll end on the midline. I know that typically the sine curve looks like this. So halfway between the start and end of the wave is the middle of the wave. I go halfway, 1, 2, 3. There's the middle of my wave. I have the crest of a wave and the trough of a wave. I know that this height here is going to be 2 because that is the amplitude in the formula. So I will put a line up at 2. I'll put a line down at -2. I'll make sure that halfway between this node and my next node, I hit the crest line. And then halfway between this node and this node, I will hit the trough line. That makes one wave of my curve. This is the trough line. I think this is how you spell trough. This is the crest line. This is the midline. This is one wavelength. Often we'll be asked to graph 2 wavelengths, so we're going to count 6 more. And halfway gives us the midpoint. Halfway between that gives us the crest. Those. Halfway between those gives us the trough. We connect those. And there we have 2 wavelengths of the graph. So we've talked about dilations now, but we also have to talk about translations. When these are vertical, they are called offsets. When they're horizontal, it's called a phase shift. These terms are only used for repeating functions, so like trig functions. You're not going to talk about a phase shift for like a polynomial. That wouldn't make sense. You wouldn't talk about a phase shift um, for your college algebra class. Okay, so let's combine a few things. Do 3 sine of 2 um 2 pi x plus pi over. Should we do over something or should we do? Let's do plus 3 pi. Let's do um let's do plus let's just do plus pi. And then let's do plus 1. Okay. So here is the most complicated version of this problem that you will possibly see. Okay. So this here has all 4 types of transformations. We already talked about amplitude changes. This one has an amplitude of 3. It also has a wavelength. Uh, the length th. It has a wavelength of 2 pi over. We look at the coefficient on x, 2 pi. Great. But now it has the other two. We have an offset, which is going to be that, so up 1, and it has a phase shift. Not an S. Phase shift. The phase shift is determined by these two numbers together. Okay? We know it's going to be, well, let's not get ahead of ourselves. The first thing we want to do to figure out the phase shift is we want to factor out by the coefficient on x. So I'm going to factor 2 pi out. That leaves just an x by itself there, which is what we want. We need to factor it out so that we get just the x by itself. And then we have to factor 2 pi out of this term. Well, there's only a pi there, so I factor out the pi. But to factor out the 2, I'm going to have to divide by 2. You can check to see if you did this right, because if you multiply this by this, you should get this number back. Sure enough, if I multiply a half by pi by 2 pi, I'm going to get pi. Half times 2 pi is, and I'm just factoring this number on the inside of the trig function. Once I do that, this is the wavelength, and this is the phase shift. Plus means we're going to move to the left. This is going to go left by 1/2. And yes, it might seem counterintuitive. Positive will go that direction. Negative will go this direction for phase shifts. Okay? So it's going to be left 1/2. Our offset is up 1. Our phase shift is left 1/2. Let's show how to use this information to graph our function. So, first off, we draw our axes. That will do for us. Then the next thing I want to do, the way that I graph these is I do the offset first. So I'm going to go up 1 and draw my midline. From there, I'm going to count up and down by the amplitude. So that's 1, 1, 2, 3. Up here is my crest line. Count down 1, 2, 3. Here's my trough line. After I have my offset and my amplitude taken care of, I want to do the phase shift next. We're going to go left 1/2. So normally we start on the midline there. But because this is shifted left a half, I'm going to go left half a unit, and this is where I'm going to start my sine curve. I'm going to then count off my wavelength. My wavelength is 1, so I count 1 unit over, which is here, and I know I complete one full wave in that distance. The sine curve generically looks like this, so I'm going to have the upper part of the wave and the lower part of the wave inside of this region that I have determined. So I put a point halfway. I put halfway between these 2 points, I put my crest. Halfway between those 2 points, I put my trough. And then I'm going to go up to the crest, down to the node, down to the trough, up to the crest. And I can do this again. So this point here is the point 1 half comma 1. This point up here is the point -1/4 comma 4. We can draw another wavelength if we want. I'm going to count over 1 unit to here. This is now going to be 3.5 comma 1. Halfway between these points is going to be another node. Halfway between these 2 nodes is a crest. Halfway between those 2 nodes is a trough. And I go up to here, down to here, down to here, down to or up to there. This is going to be the point. This is going to be the point 5/4 comma -2. This point here is 1/4 comma -2. This is the point 3/4 comma +4. And we get the idea. We can label all of those points now using this information. And then once we have our graph, we can check that with Desmos. So if I were to plug in what I just said into Desmos, we would get this. Right, equals 3 sine of 2 pi x plus pi plus 1. Let's subscript that. And if I look at this here, I notice that I do indeed have a crest line at 4. My trough line is at -2. My wavelength, I complete one full wave between this point and this point. Notice that they are 1 apart from each other. We have point 0.05409. We have 1.05409. Those are 1 unit apart in the x coordinate, and one full wavelength going all the way down and all the way up between them. So we just checked that our wavelength was correct. We just checked that our crests and troughs were correct, which means we have the correct amplitude and the correct offset. It's a little harder to check to see that we have the correct phase shift, but we can do that. If we click up here, we see this point here is at -0.254, so that's -1/4 comma 4. If we look, that is what we said our the crest immediately to the left of the y-axis. We said it would be in that position, and Desmos agrees with us. So that's really nice. So now that we've practiced all of this on sine, let's go take a look at how to apply this to tangent. And cotangent's going to work the same way. Okay. So when I am going to graph a function. And I'm going to graph a tangent function, and cotangent works exactly the same way. The first thing I have to do is have the shape of my trig function in mind. Okay. Step one is the shape. Step two is to find features. And then to graph in this order. Step A is going to be to put the offset. B is going to be to put the crests and the troughs. Which use the amplitude plus offset. The next thing I'm going to do is graph the phase shift. And the last thing to do is to graph the wavelength. So for tangent, I recognize that the typical shape of tangent starts at 0, 0, so on the midline, and then it goes up through the equivalent of a crest line is a little bit different for tangent. But there's a point here. That point is the point pi over 4 comma 1. That's the equivalent of the amplitude slash crest line of the tangent. Then we have an asymptote. Then we have this point here at 3 pi over 4 comma negative 1. And we come back up to 0. That's the full wavelength for tangent. It will repeat itself after that. If you can graph that section of tangent, you are good. So that's what I mean by the shape. You can, if you know the shape of all 6 of your trig functions and their basic forms, that is step 1. So if I want to graph, say, y equals 1/2 tangent of, let's say, 3x plus let's say 3x plus I don't want the fractions to be too terrible. But let's say 3x plus 3 pi over 2. That shouldn't be too bad. And then maybe plus 1. So I look at this and I say, I understand the shape of the tangent starts at 0, 0, goes up to an asymptote, comes up from negative infinity, hits 0 again. This is the general shape. Now I need to find the features. The features are going to be amplitude is 1/2. The wavelength is going to be 2 pi over 3. Offset is going to be up 1. It's just this number here. And the phase shift. Well, we're going to factor the 3 out of this. So we're going to get 3x plus 3 pi over 2 factors as 3 times x plus pi over 2, which means we're going to go to the left by pi over 2. So now that I do that, I graph it. I first look at the offset. Offset is up 1. So I'm going to put an offset line here at 1. Next thing is to put my crests and troughs. The amplitude is this 1/2. I'm going to go up a half. Maybe I should have made the line a little bit higher. I'm going to make my offset line a little bit taller just to make it not as small of a graph and as hard to read. Let's put 1 there. So now I'm going to do my offset line is here at 1. Mark that as y equals 1. My crest is going to go up a half from that. So let's say here. So 1 plus a half is 3/2. 1 minus a half is 1/2. There's my crest and my trough. Next step after doing crests and troughs is to do the phase shift. My phase shift is left pi over 2. So I'm going to count over here. We're going to say that this is negative pi over 2. And I know that from my tangent graph, it starts on the midline, goes up, and then comes up from negative infinity. So I'm going to start on my midline. After I graph that, I need to use the wavelength. Wavelength is 2 pi over 3. So 2 pi over 3 minus pi over 2 gives us 4 pi over 6 minus 3 pi over 6 equals pi over 6. So I count over to here. This is the point pi over 6, comma 1. That's the end of my wavelength. Halfway between these two nodes, I will have my halfway between those two nodes, I will have my asymptote. So this is 3 pi over 6 to the left, 1 pi over 6 to the right. So here at negative pi over 6, we have our vertical asymptote. And then halfway between pi over 6 and negative pi over 2, that's an interesting calculation. Let's see. So halfway between those, we get negative pi over 6 minus negative pi over 2 gives us negative pi over 6 plus 3 pi over 6 gives us negative 2 pi over 6, which is negative pi over 3. So that means here at negative pi over 3, we're going to hit our crest line, the point negative pi over 3, comma 3.5, 3/2. And we go off to infinity. We come up from negative infinity, halfway between negative pi over 6 and positive pi over 6 is 0. So we're going to hit, there's our trough, and up to there. That's one wavelength. And we can continue that if we count over one more wavelength, which is 2 pi over 3. 2 pi over 3 plus pi over 6 is the same as 5 pi over 6. So let's count 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. That's going to be one more wavelength. 5 pi over 6, comma 1. Halfway between those things, we're going to get halfway between pi over 6 and 5 pi over 6. We add those together and we divide by 2, we get halves. Going to be here. We're going to get our asymptote at halves. And then halfway between pi over 6 and pi over 2, going to be pi over 3. So we're going to have our crest here at pi over 3 comma halves. Go up to our asymptote. Here we have at pi over 3. Going to hit pi halves. And now we have 2 full wavelengths. Label everything. This is 0, 1. I think that we have now labeled most of our points. That point. Okay. Oh, I have a question in the chat. For the wavelength for tangent is different from the wavelength for sine and cosine. So for sine, cosine, secant, and cosecant, the formula is wavelength equals 2 pi over b. For tangent, cotangent, it's wavelength equals pi over b. Yes. So sine, cosine, secant, and cosecant. The formula is wavelength equals 2 pi over b. For tangent and cotangent, it's wavelength equals pi over b. So for y equals sine of 2x plus 5 minus 2, wavelength equals 2 pi over 2 pi. For y equals 5 tangent of 13x minus 5 over square root of 3 minus 4, wavelength equals pi over 13. Hope that helps. Fun having a viewer. Often students just watch this after the fact. A lot easier to answer questions while it's going. Let's see. So I think we made it through all of the homework questions that I got through Canvas, and we just addressed the comment in chat. Oh, how did we get 3 pi over 2 for the tangent function? Let's take a look at that. So the tangent function that we were graphing here had a 3 in this location. I'm going to copy this down lower. Look at it again. It was y equaled 1/2 tangent of 3x plus 3 pi over 2 plus 1. So to calculate the wavelength, we're just going to look at the coefficient on x. We get pi over 3. That what we had earlier? Did I mess it up on the live stream? I hope not. Let's take a look. Oh, yeah. Oh, no. We used the wrong formula. Oh, my. I am sorry. Well, the graph looks the same except everything is smushed in half the wavelength. So, yeah, that's a problem, and I don't really feel like fixing it. I I think that the important thing was the the process, to be honest. Um, we made an error here. It's going to be quite a bit of work to fix that on this graph, and we probably should. I probably will fix it, but um, all of the steps that we did are still going to be the same, with the exception that all of the distances that we measure should have been well, all of the horizontal distance that we talked about should have been half the size. Okay. And this is why, as you're practicing for this test, it's really nice to just, after you do it, throw it into Desmos, see if it works. Okay. So, okay. So we have our tangent function with the correct wavelength now. Amplitude is still 1/2. The phase shift is usually written as a phi. This is the Greek letter phi. Pi over 2. And the offset. I don't know what a common symbol for offset is. I think I've just been using D. Like I've been using A for amplitude, B for this coefficient, and then phase shift is this symbol, but I've been using a C for the actual constant. B is going to be 1. So it's going to be up 1, left, pi over 2. Amplitude is what it is. Wavelength is what it is. So now when we graph this, it should hit horizontally instead of vertically. Anyway, we look at the offset first. Up 1, make this 1. And we're going to go up 1/2 and down 1/2. So now we have y equals 3/2, y equals 1/2, and y equals 1. After we handle our offsets and our amplitude lines, then we're going to do our phase shift. This is left by pi over 2. So let's put that here, pi over 2. We are doing a tangent. That means we're going to start on the midline here. We have a wavelength of pi over 3, not 2 pi over 3. So pi over 3 gets us not all of the way to our whole wavelength fits into there. This is the time when you probably have to say, I need to zoom in my graph because that's not a lot of space to work with. So, yeah, let's do a little bit of erasing. Zoom in a little bit on our picture. That's just not a lot of space to fit a full wavelength event. Okay, let's put pi over 2 over here then. And let's put pi over 6 here. So there's the end of the wavelength. There's the beginning of the wavelength. Halfway between these two, we should have an asymptote. Halfway between pi over 6 and pi over 2 is, well, we add them together. Negative pi over 6 plus negative pi over 2 gives us negative pi over 6 minus 3 pi over 2, and then we divide that in half. So if you take two numbers, add them together, and divide by two, you're taking the average, but that also finds the midpoint between the two numbers. So, like, two ways you can find the midpoint are you can either find the distance between the two numbers by subtracting, and then you add that to the one of the numbers to get to the other one, get halfway to the other one, or you can add the two numbers together and divide by two, and that also finds the midpoint. So that's what I'm doing here is I'm adding the two numbers and dividing by two. That'll find the halfway point. So I do this, I get 3 pi over 6. So that gives me negative 4 pi over 6 over 2. I can cancel a 2. So I get negative 2 pi over 6, which is negative pi over 3. So that tells me that this line here is x equals negative pi over 3. And then halfway between negative pi over 3, pi over 2 is going to be same thing. If you add the two fractions together and divide by 2, you get halfway. It's going to be 5/12. So up here, it's going to be 5 pi over 12, negative 5 pi over 12, comma, 3 halves. This one over here is going to be, let's see, halfway between pi over 6 and pi over 3 is just 2 pi over 12. This is 4 pi over 12. So it should be 3 pi over 12, pi over 4. Yeah, that makes sense. So this here is going to be the point pi over 4. Where can I write that? That's pi over 4, comma, negative pi over 4, comma, 1/2. Go up like this, up from here. There's one wavelength. And we do the same process to find the other point in the wavelength. So, sorry, the other points in the next wavelength. There we go. So this here is one wavelength. We can find the next wavelength. Let's see. So between pi over 2 and negative pi over 3, that's a distance of pi over 6. So that means that, oh, we can just look at the wavelength. Wavelength is pi over 3. So negative pi over 6 plus pi over 3 is going to be positive pi over 6. That's one full wavelength. Halfway between that is x equals 0, which is going to be our asymptote. From this asymptote and hit here. This point here is halfway between 0 and pi over 6, so that's at pi over 12. This point on the crest line is halfway between negative pi over 6 and 0, so that's going to be point negative pi over 12, comma, 3 halves. This is positive pi over 12, comma, 1/2. And there we have two wavelengths of the tangent graph with the correct wavelength because we used the correct formula this time. Okay. Okay, so we have answered all of the questions that I saw today, and we've been going for just over an hour now. I think that we'll call that good for tonight. I'm going to do another hour live stream on Wednesday. I will start with questions that I'm sent, and after that, I will go over the questions from quiz 3, because quiz 3 is going to be your study guide for the test. So, yeah, I will I will do that one on the live stream on Wednesday. Feel free to use that as your study. Um, well, like you will do quiz 3. It's for points. It's an assignment. But feel free to watch along with me as I do the questions from quiz 3 as you prepare for the test, because the test is going to look a lot like quiz 3, maybe not exactly, but pretty close. Also, if you haven't used Proctorio before, you might want to brush up on that. It's how we're going to do all of our tests. So, anyway, I wish you all the best. If you have any questions, please send them to me. Oh, looks like we just got a new inbox message. Let's see if that has anything to do with the live stream. Oh, yeah. We have one more question. Let's do that before we say goodbye. So, well, if I open that up, it's going to open up directly on the screen. That's not the gonna open up in .NET. It's not going to open up in Paint.net. Good. Okay. Okay, so I was told to look at question 24 on this, I think. Question 24. Okay. And I don't see any identifying information, but might as well not put it on screen. So here's the problem. Oh, okay. Problem. There's no description. It just says 24. Let's change to black on that. 24 is y equals 2 secant of pi over 4 x plus 1. I'm assuming this is graphing this. Let's see. So it's section 2.2, number 24. Open up the textbook. Let's see. Copy of the textbook. Might be it. Oh yeah, this is the textbook. Okay, so scroll down to 2.2, number 24. The cat is so meowy right now. I don't know if you can hear the cat, but the cat is meowing at me. It's gonna get fed in 13 minutes. Yeah, so the description of the question says graph 2 full cycles of each function, state the period and asymptotes. If applicable, describe the horizontal shift and vertical shift. So, horizontal shift is what your textbook says. I'll probably always call that phase shift. Vertical shift is what I typically call offset. That's what they'll be called if you do like electrical engineering and you're measuring waves of current through wires, or if you're doing like audio engineering and like measuring sound signals being sent to speakers. So that's where I learned. Well, that's not entirely true. I did take trigonometry before I took um, analog electronics. But for me, like a lot of times, I think of trigonometry in terms of the electronics class that I took. Um, okay, so we just want to graph 2 wavelengths of this. We're going to have to state the. It says state period, asymptotes, and shifts if applicable. Those are all things that just the way that I graph, you have to find them first in order to graph. So let's do that. Amplitude. So I do have to have in mind that the general form of a secant curve looks like this. Starts on the crest, and it'll end on the crest too, because all waves will start and end where they in the same y value. Amplitude of this is 2. The wavelength is going to be 2 pi over 4, which is 2 pi times 4 over pi, which is 8. The phase shift you have to remember that the phase shift can only be read after you've factored. So since the coefficient on x is 1 after factoring, this number is our phase shift. So positive means left 1. There is no offset. Okay. Now that we have all of our features and we know the shape of the basic graph, we can go toward um, after we do that, we can start graphing. So the first step of the actual graphing is offset, which is just y equals 0. We have an amplitude of 2, so we'll count up 2 units. With the secant curve, I think that we're going to make these fairly small in um, the y directions, because the secant curves are above and below the crest line, not between them. We have that. We've taken care of our offset and our amplitude. Now we look at the phase shift. We're going to go left 1. It's good. And then we're going to take care of our wavelength. So we go 1, 2, 3, 4, 5, 6, 7, 8. We'll be fine. We're going to start on this crest line. We're going to end on the crest line. And halfway between these two, we're going to have our trough. So we count 1, 2, 3, 4. Here's halfway on the trough. Halfway between a crest and a trough, we'll have our asymptote. Same thing over here. Halfway between the crest and the trough is an asymptote. So this is at x equals 1 and x equals 765. This point here is at 1, 2, sorry, 1, 2, 3, comma, -1. This one here is at 7, comma, 3, 2, 2. It should be -2, not -1. 2. This is -1, comma, 2. And yeah, I think that we have everything we need to get one wavelength now. Okay. And then it said we want to have 2 full waves. We started here at -1 and went to 7. If we went another 8, we'd get out to 15. That's kind of far. But we do know that each quarter wave takes up 2 units. So I can go up to 9 to have my next asymptote. That gets me 1 1/4 waves. I can complete this wave, getting me x equals -3. That's now 1 1/2 waves. And if I go 2 more units, I can hit that. That's now 1 3/4 of a wave. And let's go 2 more units. And now I have 2 full wavelengths. So from here to here is 1 wave, and then from there to here is another wave. We have the complete down to infinity upper stalactite, lower stalactite, or stalagmite. Stalactites are on the ceiling. Stalagmites are on the floor. We have two full stalagmites and two full stalactites, meaning we have two full wavelengths of the secant graph. Okay. Well, now with all of that, I think now we'll call it done. As we did get that last question that was submitted during the live stream. Where did it go? Huh. Well, there was a question that I caught and we got it, and that's great. I'll see you all on Wednesday. Hope that this was helpful, and I'm glad I have it set up so it works now. So, next one's on Wednesday. Good luck on the test. Hope you all study well for it.